Hey, it's Mr. K doing a video for AP Physics 1. We're looking at Walter Lewin, Dr. Walter Lewin, lecturer at MIT, very famous for doing the most practical examples, stuff that I do in class as well. But just giving you another resource. If you want to watch his lectures from MIT, there are a bunch out there. Just look up lectures by Walter Lewin. You can find some straight from MIT, or other people have uploaded it as well. This is a lecture on conservation of energy, as you can see. And let's just play it out. So he is holding this wrecking ball. He's got it attached to the ceiling with a cable. He's holding a wrecking ball to his chin. And
3, 2, 1, 0. Ah! Ah! Physics works.
Every time. All right, so back to it. If we go back, looking at his example, what we see is that we start off with potential energy, gravitational potential energy, and as the pendulum swings down, it gains kinetic energy. It loses that potential. Work is done on it by gravity, and it gains speed as it swings down. And as it rises up the other side, it will gain that gravitational potential again. The only thing that's really taking any energy away here is any kind of air friction, any kind of, like, maybe some stretching of the cable itself, some of that bending of it. But there is nothing giving this object more energy. And so because we can trust in the conservation of energy, that means that if I were there letting this go, I'll probably try to do this in classroom with Carl. If I let it go at my chin, it should swing away and swing back no higher than the level that I let it go from. Now the key here is to not push it, because if I push it, then I am doing additional work on the ball, or he's doing additional work on the ball, and it should come back and swing up higher than what it initially started at if we do enough work on it to get it that much more energy so that it swings back to a higher level. So conservation of energy, we're going to start there. Just love to show these videos though with professors that they're old guys, but they know their stuff, and sometimes the simplest demos are the best. All right, so we'll do some problems now.
All right, so we just watched a video with Walter Lewin, and it was all about conservation of energy. So please check him out, Walter Lewin, MIT professor. Who else? Dr. Feynman is another notable lecturer, famous lecturer. Even old videos of Einstein, if you can find those, just to be shown or subjected to or exposed is a better word. Just other lectures that are out there. Me, I am your high school physics teacher. There are many lectures that are greater than I. And you should definitely check them out. So, law of conservation of energy. As you might already know, energy cannot be created or destroyed. Now, we can get energy from mass, but that's not really creating energy. You can just consider mass to be a really condensed form of energy. So, no matter what, we should be able to account for all of our energy. If we can't, you probably lost some due to heat. Friction will often take away energy from us. It really depends on the system that we set up. But if we set up a system of, just a singular object, if this were the system, if it were to move faster, then that would be from a force outside of the system. That would be giving the system energy, which is called work. But really that came from, the universe, the force of gravity, and that's just a potential energy that we can use later. So let's do a problem. Let's do the problem that Walter Lewin was showing us with the pendulum. And let me go ahead and set this up with inches just to make it easier on myself. Let's set it at 3 inches. So here is our string. This string is going to be 3 inches, or I'm going to say that's 3 meters for him. It was attached to the ceiling. And he had this mass here. And this mass, let's say it was like 20 kilograms. It was like a wrecking ball. And so maybe he had this at some angle oh, let's just say that it's 30 degrees just because, without really calculating it, and he let that thing fall. And when it fell down, then it ended up down here. And what we should know is that down here, it's still 20 kilograms of mass, but now it's moving. And if we wanted to talk the forces on it, a little bit of a throwback to forces and kinematics, there would be a force of gravity down on it. We'll call it mg. And we would have a force of tension on it, but it would be a bit greater than the force of gravity because it's moving in a curve, which means we need centripetal force, and that centripetal force would be this force of tension here. And so if we did the sum of all forces, it would be your force of tension minus your force of gravity is equal to a net force, which would be your centripetal force, which is mv squared over r. So, wait for it. There it is. So, so that's forces, that's old stuff. Let's do the new stuff. Let's do energy. So if we identify the energy that's here, in the beginning, when Dr. Lewin placed that wrecking ball to his face, and as Peebs places a tennis ball at my hip, go put it in your ball thrower. Then you have this potential energy due to gravity. We'll use the letter U for that, and that's going to be mgh, or mg delta h. If we set it as mgh, we need to identify a lowest level of energy, which would be a height of 0. And we're going to say that the thing swings down, and it is going to be at the lowest height possible here. So let's see if we can't get that shadow a little bit better. And so down here, the height would be 0. Up here, the height is something. It's going to fall down this level of h. And we could find that using trigonometry, but let's not just yet. As we fall down, we have work done upon us. We have a force applied to us. And we could use kinematics and forces, except for the fact that the force is changing. Or at least the component of force that's making us accelerate is changing. And so it's going to be a little bit difficult to do that with traditional kinematics and forces, so we use energy. So we start up here, potential energy. Down here, we got this thing called kinetic energy. It's the energy of motion. It's 1/2 mv squared. If we can neglect air friction, which I think we can in this case because the object was so dense, then we really don't lose any energy at all, and we can set one energy to equal to the other. Now in the end, this thing, or actually midway to the end really, this thing swung up to this side on the right, and it would then regain its gravitational potential energy, UG. It would swing all the way back and all the way back up to his face. Now he is confident that it won't smack him in the face because, one second. Okay. Because he believes and trusts in the law of conservation of energy, where energy cannot be created or destroyed. So if we have potential energy and it converts to kinetic energy back to potential, back to kinetic, back to potential, it should not come back any higher than what he had in the first place. So if we have a statement of energy, we could say that energy in the beginning should be equal to energy in the end. Or energy at one point should be equal to energy at another point. And what we can say is, if that's true, we can figure out the velocity of this object as it's moving down here. And we can say, in the beginning, our energy was mgh, and that's going to be equal to 1/2 mv squared. There should probably be a delta in here because it's going to change height. And what that shows us is that the mass really does not matter. And it comes up to, let's multiply both sides by 2, 2gh, delta h, is equal to v squared, or the square root of the whole left side is equal to v. Now, that's very, very simple. We're going to show that we've been using an equation that's similar to this the entire time. It might upset you, but we have been. So if we knew the height h, then we can plug that value in here to find the velocity at the very bottom. And to do that, we would use something that we would probably, I'm going to do a throw forward here to momentum. When we do ballistic pendulum, we would do a problem where we needed to find the height. And so to find the height, just to show you a little bit of trig real quick, we're not going to really solve it, but we will derive it. If this string does not stretch, if this cable does not stretch, then this makes now this weird kind of triangle where really if we look at this right triangle here that we had in the first place with our initial position and part of our final position minus that height h, we can find this length here, which is just going to be L cosine theta, and take that out of L. And so the height would be L minus L cosine theta. And for you all watching this video, thank you, because this is going to help you out on a lab in the future when we do ballistic pendulum. So based on knowing h, we can plug it in and say that 2g L minus L cosine theta square rooted would equal to the velocity of this object at the very bottom. And this is, again, conservation of energy. Another classic conservation of energy problem is the problem of the roller coaster. And the roller coaster, very simple, something like this. I think in the past we would have done one with a loop in it, but right now let's just not. Here is our roller coaster car, here is our roller coaster car, here is our roller coaster car. And we have points A, B, and C. And let's say that this roller coaster was brought up to the very top of this hill, and it's probably moving a little bit. It's got a little bit of velocity to it, and we can say that it has, since it has height, let's call that HA. This is going to be HC. There is no height at HB, but it has height here at HA, so we would say it has some potential energy due to gravity, and it has, not equals, but plus the kinetic energy of whatever velocity it has at the top there. Now at the very bottom here, we have kinetic energy only, because we're going to call that the lowest point, no more potential energy left. There are cases where we're going to call potential energy 0 at the bottom of the hill, and then for planetary problems, we're going to call potential energy 0 at infinity. It's going to be kind of weird, but it'll work out a lot better. So look forward to that. But the potential energy page, stop. You squeaky. All right. So potential energy and kinetic energy at the top equals kinetic energy at the bottom. And in here, we're probably moving still potential energy plus kinetic energy again, but definitely different amounts individually, but the same total because of the law of conservation of energy. You can always conserve your energy unless, unless for the system, there's a force from outside of that system, and then that force would do work to either add energy to the system, which would give us more, or take energy away from the system, more likely, which will give us less. Usually that's in the form of friction. Turning energy into heat. So, whatever. So if we wanted to talk about the energy at the beginning compared to the energy, let's say at point C, we would say the energy at A is equal to the energy at C. We could even have it equal to the energy at B if we wanted to. And then we would just state the types of energy that we have. At A we have potential energy, gravity, and kinetic energy. And then that's equal to the energy at C, which is also potential energy and kinetic energy. But that's at C, and this is going to be at A. Okay? And then we would just put in the equations. Say potential energy due to gravity is mgha plus 1/2 mv squared at A equals, not plus, equals mgh at C plus 1/2 mv squared at C. And so now what you would see is all terms have mass, which means that all of the masses cancel out. And then let's say we're looking for the velocity at point C. We would just move GH to the left side. So I'd have GHA minus GHC plus 1/2 velocity at A squared is equal to velocity at C squared. And then I don't really like fractions too much. If I can avoid them, I will. So let's multiply everything by 2. And if you do that, and let's say we extract that G there, G, call it the delta height, the change in height, really. Put a 2 next to it because we multiply everything by 2, plus initial velocity squared is equal to final velocity squared. And that's very familiar because we have an equation that says Vf squared equals V naught squared plus 2ax, and that's kind of this equation. It's an energy equation. Dang it, which makes things easier because we don't care about direction. Did you notice? We didn't care about all these changing direction values of velocity. We won't care. Energy does not care about changes of direction. It just cares about changes of position. So that'll help us out. We're going to definitely work much more with that. But you need to be able to account for the different types of energy in your problem. Now, let's say, for instance, maybe we had friction. And friction would have done work on our system. And so we would instead add one more term here, which would be the work done by friction, however much energy we would have lost. And at the very end, we would still have that, and we would be working with that value at the very end. Now, that's confusing to some students because they're wondering, why is it positive? Because didn't friction take energy away? And it did. But we need to be able to account for all of it. So if we're summing up all the energy types at different points in the problem, we should be able to sum up and add together all the energy in the end, which should equal all the energy in the beginning. So we'll stop it there. We will talk much more about energy in the coming days. It's going to make problems a lot easier, I think. So until next time.